Hi everyone, my name is Paul Mitcheson from Imperial College London, and it's a pleasure to be able to talk to you today about high frequency inductive power transfer. Before we get started with the tutorial, as I'm standing in my laboratory at the moment, I thought I would just hand over to one of my colleagues, Juan Artiaga, to say a few words about what we do here in the lab.
Hi everyone. My name is Juan. I'm here working on some characterization of a high frequency inductive power transfer link, and I hope you all enjoy the tutorial. Back to you, Paul.
Right, here I am back in my office and we can start with the tutorial. So, as you know, I'm going to talk to you about high frequency IPT. What I want to do here is to obviously cover some basics associated with the magnetic link and also the circuits. And I'll also try and perhaps draw out some of the differences between the sort of stuff that we do in high frequency IPT versus the lower frequency stuff that you will have seen covered in the previous talk by the guys from the University of Auckland. So I thought I would start by saying a few words about how I got interested in IPT in the first place. Well, actually, prior to that, I'd worked a lot on energy harvesting. And then in, I guess it was around 2007, 2008, I became aware of some work that had come out of MIT. This is the team here that had actually went on to found Witricity. Now, I know there's a lot of work that happened in inductive powering obviously before this work was published by these guys at IPT, but I thought it was quite a striking photo, and in particular you can see here in this IPT system that there is a very considerable distance between the transmit coil and the receive coil that's obviously big enough to fit the whole team in between the coils. And I thought that was quite an impressive demonstration. One of the interesting things there is this is actually what we would refer to as a high frequency IPT system. It's operating in this case at about 10 megahertz. Okay, so I'm going to talk to you about several aspects of high frequency IPT here. I want to talk about the inductive link itself. I know you've heard already quite a lot of information about this from the previous talk by Dulipa and Grant in the introduction to IPT. I'm going to talk about that again, covering a few of the basics, but quite quickly. And I want to try and say a little bit about how we optimize links for operation at high frequency. And throughout that, it should become clear to you why high frequency IPT, by which we're talking about operating at multiple megahertz, has some advantages in certain circumstances over the lower frequency stuff that you've heard about just now. Of course, there are caveats there, and there are advantages and disadvantages to both aspects of the technology, and where you end up deploying one or the other is going to be very application dependent. Then I want to talk to you a little bit about the drive circuits, the electronics and the power electronics configurations that we tend to use at these frequencies are a little bit different to what you might be used to seeing if you've come from a sort of standard power electronics background. I'll do the same with rectifiers. I want to also talk very briefly about regulations. This is something that there is a dedicated talk on in this school by Mario Feliziani, so I would encourage you to look at that. I'm only going to give you a very brief overview there and then refer you to the talk by Mario Feliziani later on. Okay, so first of all then, let's talk a little bit about what is high frequency IPT. So clearly, high frequency, well, the stuff that you've heard at the moment, primarily focused on electric vehicle charging, is operating at around 100 kilohertz. The Qi standard operates at around 100 kilohertz. And what I'm talking about here are systems that operate typically at 6.78 or 13.56 megahertz. The reason for those numbers there, 6.78 and 13.56, they're very specific. And you may, if you're not familiar with some of the standards here, you may think that they're rather arbitrary numbers. They're not actually arbitrary. They are the ISM bands, industrial, scientific and medical bands, where we have unlicensed operation. In other words, we are free to use those frequencies in inductive power transfer. So that gives us the opportunity to significantly step up in frequency and try and operate, again, a near field system. We're trying to minimize radiation. It's got to be an inductive system in order to be efficient. we're trying to therefore see whether there might be some advantages of operating at these higher frequencies. The advantages that we would generally cite, and I will show you some demonstrations that we've built in our laboratory towards the end of the talk, are that we can generally get greater air gap distances, generally due to higher coil Q factors, and we also have lighter coils than in lower frequency systems. Now, clearly I'm giving you the benefits here as I see them. It's not quite also simple because there are also some disadvantages with operating at high frequency, particularly perhaps sometimes in higher power applications related to regulations, and also in general the containment of the magnetic field once you move to these higher frequencies and you use coreless coils, so we only use air cored coils rather than coils with ferrite present. Then there are perhaps issues with the magnetic field coupling into unwanted objects. There's a consortium in industry for MHz IPT, and it's called the Air Fuel Alliance. So let's talk for a moment about the inductive link itself. What you see here on this slide actually is the first system that we built at Imperial, and that was back in about 2012. And air cored coils, as you can see, they're actually made from copper plumbing pipe. We then built an inverter to go on the transmit side and a rectifier to go on the receive side, and we built our first high frequency wireless power transfer system. Just in case you come at this really, as many of you probably will, from a background in more traditional power electronics, then what we're essentially talking about with an IPT system is operating a transformer but removing the former part of the transformer. In other words, the core is removed and I end up with a primary coil and a secondary coil, and unlike a transformer where the coupling factor, the fraction of flux produced by one coil that links with the other coil, is very high, in an IPT system it's very low. And I think typically when you look at lower frequency IPT systems, you might be operating typically with coupling factors of maybe 20 to 30%. Here we might, in higher frequency work, we might typically be operating with coupling factors that are as low as 5%. And you can see here a definition of the coupling factor as being the mutual inductance between, divided by the square root of the product of the two coil inductances. And you've seen that in the previous talk. It's useful also, I think, to take what you would have seen in any first class you did on power engineering and you covered transformers, just to refer back here to the equivalent circuit model that you're all familiar with on modeling a transformer. This model isn't necessarily tremendously useful when it comes to analyzing IPT systems, but I think it's a good point to start because of familiarity, and also because you can get some intuitive understanding as to at least what makes building an IPT system quite tricky. So as I said, in a regular transformer, the fact that you have a large coupling factor actually makes energy transfer between primary and secondary quite straightforward, because if you consider what that does to the circuit blocks here, you've obviously got an ideal transformer block in the middle of this equivalent circuit, and then you've got some leakage inductances on either side. You've got a magnetizing inductance, some hysteresis loss associated with that magnetizing inductance that's modeled here on the primary. Now, in a regular transformer, obviously you want to make the magnetizing loss as low as possible. And you end up with a magnetizing inductance that is quite large. After all, this is wound onto a magnetic core, so that inductance can be quite large. And the leakage inductances are going to be pretty small. The coupling factor should be, on a well-built transformer, 98% or so or higher. And what that means is when you drive the system with a voltage on the input, the vast majority of that voltage gets transferred onto the air gap, VAG, and also the vast majority of that comes out at the output, and therefore you end up with a voltage ratio that is almost exactly the same as the turns ratio on the transformer. Now with an IPT system, it's rather different, because only a small fraction of the input voltage actually appears across the air gap, because now, once we remove the core of the transformer, the leakage inductances start to dominate. The magnetizing inductance, as drawn here, is quite small. The amount of coupled flux is quite small. As I mentioned, in a high frequency IPT system, it could be as low as 5%. So these leakage inductances are large, and I have now a potential divider formed on the primary between the leakage inductance and the magnetizing inductance, and on the secondary I have also an extra series resistance in there of the leakage inductance, which can be quite significant and take a significant fraction of the voltage on the receiver before passing it on to the load. So this is an issue, because if we want to get therefore decent levels of power transfer across one of these systems, it means that we're going to ultimately have to drive this system with a very large voltage, and we don't want to have to do that by putting on massive voltage ratings on the semiconductor components that are both driving this system on the input and are receiving the power on the output. One of the things that often comes up with many people that have not looked at inductive powering before, common misconception is that low coupling means poor efficiency, and that's not the case. You'll see a little bit more later on if you haven't twigged that already from what you've seen in the previous talk. So I want to talk a little bit about modeling, because in all IPT systems, the design of the circuits is very related to the characteristics of the link. And so it's important that we have a good model of the link. As I mentioned on the previous slide, the regular model of a transformer that you use is not necessarily the most useful one for you to take forward when you're working on IPT. It's better to use this coupled model here, where we have a primary and secondary inductance, a coupling factor between them, and RP and RS represent the primary side resistance and secondary side resistance of the coils, and we've got an impedance then connected to the secondary side called Z secondary. And so we go right back to basics, and the voltage induced, the voltage across the primary coil is just its self-inductance multiplied by dIdt plus its mutual inductance with the secondary multiplied by dIdt on the secondary, and that's really back to absolute basics of electromagnetics. The reason that we're interested in going back to this type of model rather than the one that I've shown you on the previous slide is that here we can just talk now about there being one inductance on the primary and one inductance on the secondary. And of course, these are actual physical components in your IPT system. If you can build a model that just uses that, rather than, and obviously coupling factor as well, but actually the real physical components are now in the model, rather than splitting them out into different parts depending on whether it's a magnetizing inductance or whether it is a leakage inductance, actually is very beneficial, because they're things you can measure directly in the laboratory, and they are component parts that go into your circuit architectures. It's also easier to model in SPICE, because this coupled model of inductance here is the way that you input data into SPICE for modeling this type of circuit. What we then can say is that actually we split the voltage across the primary and secondary inductances into the voltage across the self-inductance plus an induced voltage which comes from the current in the other side of the link. In other words, if a current flows in the secondary, the coupling of the magnetic field from the current that is creating that magnetic field in the secondary couples back into the primary coil and generates a voltage in the primary coil. And of course, that is exactly the mechanism by which we're transferring power back and forth from one side to the other. So here we're breaking the coupled inductances into self-inductances in series with some coupled sources, epsilon P and epsilon S in this case, that are, of course, epsilon P is a function of the secondary current and epsilon S is a function of the primary side current. It's nice to do this because it's now intuitive and straightforward to see the effect of one side on the other, because there's a controlled source on one side that is directly controlled by what is happening on the other side of the link. Now we've got a voltage induced on one side or the other, and a current will flow through it. We can now talk about there being an impedance associated with the coupling of one side of the link on the other. In other words, epsilon P as a function of IS here on the transmit side can be modeled as an impedance, and that impedance is present because I've brought the receive side up to the transmit side and I'm coupling power across. In other words, the voltage induced on the primary by action of current flowing in the secondary looks like an impedance that is introduced into the primary side circuit, and consequently that is a mechanism by which I'm transferring power in this model out of the primary side into the secondary side. If I make that impedance real, it's a reflected resistance rather than a reflected impedance, and that's a mechanism for power real power to flow from the transmit side to the receive side. We can calculate the reflected impedance just looking here that the voltage induced on the primary is simply the mutual inductance multiplied by the rate of change of secondary current. The secondary induced voltage is just the mutual inductance multiplied by the rate of change of primary current, and if I combine those two I can get an expression here of the primary side induced voltage here as a function of primary current and the other main parameters in the system. I'm using F instead of omega here, even though it comes with the 2 pi component in the equation, simply because we're used to looking at F as being 6.78 or 13.56 megahertz when it comes to high frequency IPT. If we then divide the primary side induced voltage by the primary side current, then we can write an equivalent impedance, and that is what we call the reflected impedance from the secondary back to the primary. And as you might expect, in its generic sense, it has both real and reactive parts. What I would like to do here is to make the reflected impedance purely real, in other words, set the imaginary part to 0, because I don't want to have a transfer back and forth of reactive power across the link. As you know, any transference of reactive power must have a current flow associated with it. That current must flow through some copper, and consequently there will be losses. So I don't want to have reactive power that is sloshing back and forth across the link, and consequently I need to make the ideally resonate out, and you've already seen this in the previous talk, the inductance of the secondary in order to set the reactive part of the reflected impedance to 0. So highlighted in blue there, I need to make sure that part of the expression is equal to 0, which I can do by setting x sec. So the resulting circuits, if I then look at this as a reflected impedance, I've now got a transmit side with a reflected impedance that is a function of what is happening on the receive side. And that's very good because I'm now abstracted to a point where I can look at driving a coil on the primary with a series impedance with that coil, and that is now a circuit that I have to design a drive circuit for. Likewise, on the receive side, I can consider that I've got a voltage source which is in series with my pickup coil, my inductor, and that's going to drive power into the secondary. So it's nice to get the model to this form because now I can think about how I design the circuits based on just simple RLC types of circuit models. Now, before we go on to actually designing the circuits, I think it's important to give some consideration to why we're interested in operating at high frequency. And you can see here a well-known expression for the efficiency of the magnetic link. And it includes here a relationship, as you can see, between the square of the coupling factor between the coils and the Q factor of the primary and secondary coils, Q1 and Q2. If you plot the efficiency against K squared Q1, Q2, you can see that as you get to very high coupling factors, which would be the case in a regular transformer, or alternatively very high Q factors, or alternatively all of them being high, then the efficiency tends towards 1. And so if we can have a K squared Q1, Q2 product that is greater than 10, we will get an efficiency in the link of greater than 50%. If we have a K squared Q1, Q2 product that is greater than 350, we end up with a link efficiency that's greater than 90%. And that's the sort of thing that we're aiming for in a high frequency IPT system. The question then is, well, how do I maximize this product K squared Q1, Q2 in order to maximize the capability, the efficiency of the link? Well, one of the reasons, as I mentioned, that I might be interested in a high frequency IPT system in the first place is that actually I might be able to achieve higher Q factor coils than I can achieve at low frequency. So the Q factor of the coil is proportional to omega L. If I increase omega, I will increase the Q factor of the coil. Now that's obviously a first order approximation because in actual fact the Q factor of the coil is omega L divided by R, and as I go up in frequency the resistance of the coil will increase because of skin effect. Now what that means is that the Q factor of the coil does increase with frequency because omega L goes up faster than R because the the resistance due to the skin effect increases as the square root of frequency, whereas obviously omega L increases proportional to frequency. So the Q factor will increase until some point that the coil is no longer an electrically short component. When it starts to look electrically long, it looks like an antenna, and it will start to radiate, at which point the efficiency of the system will start to fall. So the aim is to be able to operate my systems with maximum Q factor, and you can see here this is just an example for a 3-turn coil of 10 centimeter radius. You can see the optimum frequency here is something of the order of 10 megahertz, and therefore this might be a very suitable system to operate at a frequency of about 6.78 megahertz, for instance. So as long as we operate the coils at the right frequency, then what we typically find is we might be able to get Q factors, so this is the unloaded Q of the coil, that might be up to something like 1,500. And that might be typically around 3 times higher to what you would often see in a lower frequency system. The downside is that the coupling factor will be lower, typically, than a low frequency system. We don't have all the ferrite in here, where we are creating magnetic field over a larger area typically than the lower frequency systems. But there's perhaps some advantage to that in some regards, because it typically means that I can go over a longer distance than I can with a lower frequency system. In other words, if I'm interested in the product K squared Q1, Q2, and I know that going to higher distances is going to reduce my K, I can compensate by having higher Q factors. And I can achieve those higher Q factors by going to higher frequency. It means that I'll also end up with an air-cooled system, so the systems tend to be very light. Okay, let's spend a bit of time now talking about the primary side drivers for high-frequency IPT systems. And if you're a power electronics person, you will call this an inverter. The inverter needs to take typically a DC power supply and convert it into the high frequency currents that have to flow in the primary side of the system. So to keep our systems efficient, and this is true in any power electronics, of course, we need to minimize the loss in the semiconductor devices. And there are 2 types of losses that we consider generally in semiconductor switches. There's conduction loss and there's switching loss. And if we're talking about MOSFETs, the conduction loss is proportional to the square of current, and the switching loss is proportional to the frequency of operation. Now, here's the key thing that makes design of the electronics for high frequency IPT quite a challenge. Switching loss can be a problem for circuits operating in the tens to hundreds of kilohertz. It's certainly a significant potential problem when you start operating these systems in the megahertz. And consequently, what we would like to do is to try and reduce or almost eliminate that switching loss using a technique called soft switching. The other thing that we need to bear in mind is that we don't want to be rating our semiconductor components to a massive VA rating in order to be overcoming the inductances of the primary and secondary coils. So, as I've said, conventional hard switching is not suitable really in the megahertz region, not at any reasonable power level. So we're interested in looking at soft switching types of device, and of converter rather. And there are different types of architecture that can be made to be soft switched. In other words, 0 voltage and/or 0 current switching. And the topology that most people are familiar with when they come certainly from a power electronics background is a Class D half bridge and then putting 2 of those together to make a full bridge. Very popular in lots of power electronics, and you'll have seen some of that used in the previous presentation for the 100 kilohertz types of systems. So here you see the topologies there of the Class D half bridge and full bridge, and you can see that in the half bridge obviously we have 2 transistors. One of them is a high side device. On the full bridge system we have 4 transistors, and 2 of them are high side devices. And you can see here that we've got the transmit coil, which is the inductance here, resonating with a capacitor, and then on the left you see an example there of a load being reflected from the receiver back to the transmitter. So although this looks like a nice and simple topology, one of the issues with it is that it is using 2 devices or 4 devices in the full bridge system. 2 of them are high side driven and can lead to problems with crosstalk within one of the legs, particularly switching at these high frequencies. You can see here on the top of the slide the typical Class D waveforms producing square wave voltages. The resulting current that flows is largely sinusoidal because of the high Q of the resonant tank. One of the other issues here is that you cannot tune this type of transmitter exactly at resonance, because if you do, then if there is no receiver close to the transmitter, the reflected impedance into the system is 0, and you're just left with an LC circuit that is resonating at its resonant frequency, and consequently you get very large currents that can flow. So you typically will tune this slightly away from resonance. Typically you'll operate it so that the load is slightly inductive, and at that point you can see here as you move away from resonance that you end up then starting to incur some switching losses because you've had a shift in the phase of the current with respect to the square wave switching voltage, and that will then lead, of course, to some additional losses. So what are we going to do to try and overcome some of these issues? Well, the issue where we're using multiple devices, and in particular where we're trying to avoid using high side devices, is something that we can start to consider when we look at other types of converter architecture. In particular here, taking some inspiration from what is typically used in a lot of high power RF circuits. What in power electronics we might call a Class E inverter, and what in the RF domain they will typically call a Class E amplifier. Single switch inverter, as you see on the left here. There's a resonance circuit that is hanging off the inverter. The input part of it looks a bit like a boost converter, and as long as you're switching the transistor at the right frequency as a function of the resonant network there that's hanging off it, we're pushing current in through L1, and we're getting a nice resonant action here so that we're producing a sine wave in L2. L2 here is the transmit coil. RL is the load that is being reflected from the receiver back onto the transmitter. And you can see clearly the system architecture here only uses 1 transistor and it's low side, which is a benefit. The voltage across the transistor is now shaped. It's no longer switching in a square wave fashion. It is switching somewhat sinusoidally, as you can see on the right with VDS. That means that we're not going to have uncontrolled ringing at high frequencies. We've got a nice controlled waveform, and also where we are achieving, as you can see here, 0 voltage switching of the device Q1. One of the potential improvements that we can make to this inverter is to add this capacitor C3. You'll see that this architecture here is essentially identical to the one on the previous slide, except we've added this additional capacitor C3. Now, if you think of essentially what C2 is doing here, it's providing a lot of the voltage to counteract the voltage required to drive L2 and reducing the voltage rating required of the transistor Q1. C3 is doing the same but for current, and is providing you with a nice path for the resonant current in L2 to flow. And this is a technique, you don't tune all of this exactly to resonance. This is something that we call semi-resonance, and it can be useful when you've got high currents that need to flow in L2 and you don't want to have all of that current having to flow through the transistor Q1. On top of that, though, there are some issues still with these circuits, and in particular, what we note here is that when we design these Class E types of circuit, either the simple one or the semi-resonant one, is that there is an optimal load which allows us to achieve 0 voltage and 0 derivative voltage switching. So if you look at these plots here, you can see the on the left, we have a system where you can see at the bottom of the plot, the gate is switching on and off, and you can see when the gate switches off, the voltage on the drain of the transistor starts to increase, and it increases from 0 with a a controlled gradient. Therefore, we have zero voltage switching when we turn the device off. And when we come to turn the device back on again, you'll note the nice smooth landing of the drain source voltage, and hence we're able to have very low losses when the device switches back on again. Now, unfortunately, what you see in the other two plots is as we change the value of the reflected resistance in the system, corresponding to either a change in motion between the transmitter and the receiver or just a change in the actual load resistance on the receiver, we either pull into conduction the drain body diode of that Q1, or we end up with excess voltage at the point when we try and switch the transistor on again. And these are giving us then non-optimal conditions, and as we therefore change the reflected load on the system, we can get additional losses. We can, however, still with this type of topology achieve a system that actually is quite robust to changes in the reflected load. So you can see here a class EF inverter, which again, very similar to the two topologies that I've already shown you, but in this case with the addition of this branch here, C2 and L2. In a typical class EF inverter, that would be tuned, as you can see on the diagram, to about twice the switching frequency. Actually, we don't tune in our systems to twice, we tune to about 1.5 times the switching frequency. And the interesting thing there is that this additional resonant branch here gives you more degrees of freedom. You have more component values when you design your circuit. And what we've been able to find is that there are a number of solutions now where we can actually obtain zero voltage switching for Q1 at both turn on and turn off, even as we change values of RL. So you remember in the previous slide that was not the case. Once we design this system properly with the addition of C2 and L2, we can now get zero voltage switching and therefore low loss, even as RL is changing, and that's really critical for a practical IPT system. The other thing that we get with this system is, as well as being able to design it so that it has low loss as RL changes, we can maintain a constant current in L3. In other words, we've now decoupled the behavior of the transmitter from the receiver, and even as we change the value of RL, then we create a constant magnetic field from the transmit circuit. And in this case, then, as I said, as RL changes, we're not getting additional switching loss. And you can see that in the plots here on this slide, where we now have a more complex trajectory of the drain source voltage. It has additional harmonics brought about by that additional resonant network. But fundamentally, even with different values of reflected resistance here, we are maintaining zero voltage switching in all cases and consequently high efficiency. We're also, as I mentioned, maintaining a constant current in the transmit coil. And I can show you here a scope capture as we are literally moving the position between a receiver with respect to a transmitter. And you can see here the trajectory of the drain source voltage on the transistor in yellow, and you can see a measurement here of the transmit current in green. And this is as we're literally bringing a receiver close to a transmitter and moving it further away again. And what you notice is that there is a small change in the transmitter current in green, not very much of a change, as we're changing the power throughput of the system there by bringing the receiver close. But at the same time also the trajectory of the drain source voltage in yellow is changing, but notably the points where it leaves 0 volts and returns to 0 volts, in other words, the times when the transistor is turning off and turning back on again, they stay constant, and hence we have a very efficient system with very low switching loss. And also we have the decoupling now that's required between transmitter and receiver with the constant current in the transmit coil. I'd like to spend a little bit of time now looking at rectifiers. And in particular, the first choice that we need to make on the receive side is whether we use a parallel resonance, as shown on the left here, or a series resonance, as shown on the right. And again, this is something that you've heard a little bit about from the previous talk. One of the things that I think I probably didn't mention on the earlier slide when I was talking about optimizing the behavior of the coils to get maximum link efficiency and the importance of the product K-squared Q1, Q2, The maximum link efficiency formula is only valid when I put an optimal load onto the system. And here you can see our load here. In both cases, for the parallel case and for the series case, there is an optimum value of our load that I can calculate, and you can see the formulae on the slides, that is dependent on the values of K and Q for the system that will then give me the maximum link efficiency. So really what we might want to be able to do in a system, and it depends really how practical things are, but is to try and design now a rectifier that will sit on this receive side instead of our load in either of these two cases, but which has an input impedance that looks like our load. So I need to know what is the optimum value of resistive load and then design a rectifier to emulate that in order to maintain maximum efficiency of the link. Now, in these high frequency systems, we tend to prefer the use of series resonance on the secondary. And the reason is that if you use a parallel resonance on the secondary, then if you change the value of the resistive load corresponding to a change of power throughput in the system, which will be common if you're charging a battery, you might charge it at different rates depending on its state of charge. As you change the value of RL, if you have a parallel resonance, then you will actually change the imaginary part of the reflected impedance as seen by the transmit side, and that will detune the system. In contrast, if you use a series resonance as shown on this side, and assuming that you have tuned out the secondary inductance with a suitable resonant capacitance, then actually the reflected impedance as seen by the primary is changing but remains purely resistive. And you can see here in the equations on the right, assuming you've tuned out the inductance and the capacitance with each other, then ZREF is equal to RF, that's the reflected load back to the primary, and it's only dependent here on it's dependent on omega M and RL, but the important thing is that it is at that point purely resistive. Now, what I showed you in the slides that we looked at on the inverter was we have an inverter topology, the class EF inverter, which actually is able to cope with maintaining soft switching even as the reflected load resistance changes. We've got to avoid changes in reflected reactance because we can't cope with that very well with these topologies. But if we only have changes in reflected resistance, which is possible with a series with a series tuning on the secondary side, then we can use that inverter topology and we can maintain high efficiency across the operating envelope. So what does that mean in terms of the actual rectifier types that we might use on these systems? Well, there's a difference here between whether we have a series or parallel resonance as to the type of circuit that we might want to attach on the receive side. And this really comes down to whether the rectifier in question is a voltage driven topology or a current driven topology. And here I'm really referring to the time domain behavior of these circuits. If you think that the series resonance has current flowing in an inductor, that inductor is then acting as a current source to be able to pass energy into the rectifier, and therefore I need a current driven rectifier in order to attach to that system. These topologies here that you see are pretty standard power electronics topologies. Some of the issues that you might get when you move to operating these at high frequency are related to what you might expect, perhaps diode reverse recovery, but also the fact that the parasitic junction capacitances on the diodes in this case are ultimately their average value through a cycle of operation of the circuit depends on the power throughput of the circuit because it's voltage dependent, and changes in those parasitics can then end up detuning the system for you. And then even with your best design, you've chosen series resonance, you've used a topology on the inverter that's able to cope with changes in resistance, you end up getting a change in reflected reactance as well because of the behavior of these parasitic junction capacitances, and that will detune the system. So what we might then choose to do is to use a low DVDT rectifier, so introducing the idea of resonance into the rectifier. These are class E based topologies that you see on this slide, and one of the things that you will notice here that is quite useful to us is that frequently these topologies end up putting a capacitance in parallel with the diode, and this means that the overall capacitance across the diode in other words, the value of that known linear capacitor that I add plus the junction capacitance, now sees a very small fractional change as long as the capacitance that I add is less than the junction capacitance of the diode. And consequently now that change in reflected reactance I was talking about due to the changes in the junction capacitance of the diode can be largely negated. One of the issues, of course, when you start to use resonant topologies like this is you end up with high voltages on the diodes, and consequently wide bandgap materials are very useful here. I want to very quickly now, and this will be very whistle stop, and again I point you to Mario Feliziani's talk later on about regulations and safety of these systems. But just very briefly to mention regulations, there are limits on EM field levels for protecting humans from adverse effects. There are some thermal effects and non-thermal effects. In other words, if you put yourself into a magnetic field, you will get heated up to a certain extent, and non-thermal effects include things like nerve and muscle stimulation due to induced voltages by your presence in the magnetic field. There are, within the EU and various different directives around the world, there are laws that are based largely on ICNIRP, International Commission on Non-Ionizing Radiation Protection, about the maximum magnetic field strengths that you can be exposed to. This might mean you need exclusion zones around a system. It may also mean that you operate the design in a specific way. You might need to make sure your impedance levels, your reflected impedance levels, your coil designs are such that you end up with perhaps designed for a minimal magnetic field in order to, in other words, keep the currents controlled in the coils and therefore not create an excess magnetic field in order to improve the safety of the system. Again, Mario will talk more about this later on in the school, but you can see here electric field strength as a function of frequency and magnetic field strength on the right as a function of frequency for levels from the 1998 ICNRP documentation for human safety. And the general point that I want to make here is that, of course, as you go up in frequency, the field strengths that you're allowed to be in decrease, and that could be potentially disadvantageous for high frequency IPT systems. But of course, and you'll have seen this in the formulae, you've also seen it mentioned, I think, in the previous talk, the amount of power transfer that you can get goes up with frequency anyway, so this is not as bad as it looks from a power perspective. Okay, I want to spend a short amount of time now just talking about some of the applications that we've been able to put our IPT, high frequency IPT systems into. So one of the nice things that we've done that we often take around to trade shows and to conferences is to have a very lightweight system here using a receive side mounted onto a drone here, a very lightweight drone of a copper plated ring around the plastic propeller guard of the drone, flying above a charging pad. It's a PCB based charging pad, and you can see here the drone is able to fly above that charging pad. It's tethered on a nylon tether to stop it flying away, and this is using one of our Class EF inverter systems, and you can see the trajectory of the drain voltage on the MOSFET there constantly changing but maintaining zero voltage switching, and this really is designed to show the dynamic capabilities of our system and also the lightweight nature of it. Moving away from drones now and looking at the issue of micro e-mobility, we've put a wireless charging system here onto a Govex e-bike. And you can see here, this is a ride-on scooter. We've actually built a 600-watt system here. You can see the inverter and rectifier there and the receive coil. And we actually have a paper on this in the conference. You can see the title there on the right. So I'd encourage you to have a look at the paper and the associated talk with that. This is actually using a push-pull inverter operating at 6.78 megahertz. You see some of the waveforms there. And we were able to get, for a 700-watt input, a useful 600-watt output when everything was back in place on the scooter itself. So with that, let me just bring this to a conclusion. We're using high frequency IPT in order to exploit the benefit of ferriteless lightweight coils and achieve large air gaps and large freedom of movement between the transmitter and the receiver, which is required in many of the applications that I've shown you here. Typical Class D bridges can be, and it depends very much, I stress, on the design, but can be outperformed at these frequencies by Class E type circuits. We use an EF circuit actually specifically designed to be load independent, as I mentioned, and to achieve constant current. If you want to see a sort of cross-reference between the work in the previous presentation on electric vehicle charging, then the LCL output that they use there is achieving the same type of characteristics as we're looking for here. Rectifier choice can have a huge impact on system performance and its ability to operate over a large load range. And of course, the applications for high frequency IPT are very wide ranging. So thank you very much indeed for your time. And if the technology is working properly, I guess I should now be able to take some questions. Thank you.